Okay, good morning, everybody. I believe that we're now live on this webinar. This is Denise Gabosta in Cork, Ireland, and I'm delighted on behalf of the organizing committee to welcome you to this new series of seminars focusing on high-resolution astronomy, the sharpest view of the radio universe, VLBI, connecting astronomers worldwide. We're planning 7 seminars over the coming year, up to the time of the next European VLBI Network Symposium, which will be held in Cork, Ireland in July 12th to 16th, 2021. Since this is our first webinar, I want to just mention a few logistics. We have quite a few participants today, making it impossible to take any questions verbally. You will be muted throughout the presentation, but you're invited to type in any questions you may have for our speaker through the question and answer Q&A facility. You can send in questions both during and after the presentation, and questions will be answered after the presentation. Please try to write your questions clearly and keep them short. We'll aim to get to as many of your questions as we can, and we apologize in advance if your question is not among those we have time to answer. I'd now like to invite Marcello Giroletti of the Institute of Radio Astronomy in Bologna to introduce our first speaker, Cristiana Spingola.
Hi, everyone. It's a pleasure to be here with all these people and to introduce Cristiana Spingola, our first speaker. Cristiana did her studies in Bologna, at the University of Bologna, where she got her master in 2014, working with Professor Daniele Della Casa on VLBI observations of the gamma ray Blazar. Then she moved to Groningen, where she did her PhD, which she completed in 2019, working with Professor John McKean. After the completion of her PhD, she did some postdoc, a short postdoc at Astro in the Netherlands, and then she went back to Bologna for a postdoc that she is running now since September 2019. And she will talk to us today about the view of how to use the strong gravitational lensing to zoom in on high-redshift galaxies. And I think that's all, so I'm happy to leave the floor to Cristiana.
Thanks a lot to Marcello and Denise. So I will try to share the screen. Let me see. Okay, if you can see it. Okay. Is it okay?
Yeah, that's fine.
Okay, can you see my cursor?
Yes.
Okay. Good. So hello, everybody. Thanks a lot for joining this talk. And first, I would like to thank the organizers for inviting me to start this EVN seminar series and giving me the opportunity to talk to you about what I've been doing during the last years, namely using strong lensing to zoom in on high-redshift galaxies and therefore study the smallest scales at the highest redshifts. So just before going into, let me see if, do you see the slides going on? Maybe need to do this, okay. Before going into the details of the work, I would just like to give a brief introduction on the science case of this kind of science, that is to address the small-scale challenges of the lambda CDM paradigm. So as you can see on the right, the large-scale structure of the universe from an observational point of view and a simulation point of view are quite impossible to discern. So this means that the lambda CDM model is very good at explaining the large-scale structure of the universe, while there are some tensions on the small scales with observations. So with small scales, this is what I mean with a very highly detailed view of a small scale structure of the lambda CDM universe, of our universe, that is a galaxy. And here I'm putting there just the components I will be focusing on, namely a dark matter halo, and then a baryonic component that is made by gas and stars, and this can be in the form of disks or central spheroidal like bulges. And at the very center of galaxies, we know that there are supermassive black holes, at least in the most massive one. So as the hierarchical structure process is dominated by merging that is driven by the dark matter component, this is the first component I will talk about. On the left, you can see the dark matter view of the illustrious simulation, that's high redshift, and you can see that around the most massive halos, there are several smaller halos or satellite galaxies. So the lambda CDM model predicts that there should be several satellites around the Milky Way, for example, but when we try to observe them, we do not find them. So where are these satellites? Are they too faint to be detected, or there aren't? So we need to rethink about our cosmological model. So this is known as missing satellite problem, and this is still an open question in current cosmology. Another way to understand if galaxies follow the predictions for lambda CDM model is to look at the cold molecular gas that here you can see again from the illustrious simulation. So the cold molecular gas is a fundamental ingredient in the formation and evolution of galaxies because it's the fuel for both star formation and supermassive black holes. However, the low surface brightness of the CO120, that is the tracer that we mostly use to observe cold molecular gas, it's very difficult to observe at high redshift, and therefore it's observationally mostly under constraint. So we do not know how it is distributed, but if the merger scenario works, then we should expect to observe this gas settling down into disks that are rotating. And at the very center, there should be a central star parse component, and therefore a compact, let's say, host galaxy as a merger remnant. And finally, the last ingredient is the smallest one, but the most powerful, that is composed by supermassive black holes. So here on the left, you can see the simulation where it's color-coded according to the temperature of the gas, cold, warm, and hot, as shown on the top left. And you can see that there are these violent explosions into the center of the most massive halos. And these are due to supermassive black holes and especially active galactic nuclei, namely when supermassive black holes activate and outshines the light of the host galaxy. So this kind of events that we can call them into AGM feedback, so winds and jets going into the surrounding medium, have a profound effect on the rates at which stars are formed in galaxies, but also in the morphological evolution of the galaxy. And we still do not know very well how they happen, why they happen, and where they happen. For example, we do not know where the most violent events, like the gamma ray flares, happen in AGN, how much the radio jets are important into triggering or preventing star formation in galaxies. So we need to study the small scales of AGN to understand all these physical processes that can be then implemented in simulations, and therefore we can understand if we can reproduce the galaxies as they are now. So we need a high angular resolution to study these small scale effects because they are all on the sub-galactic scales. And at the radio wavelengths, the highest angular resolution is provided by very long baseline interferometry. And here we can, with this technique, we can reach resolutions at sub-milliarcsecond level when observing at the highest observing frequencies. On the right, you can see the map of the European VLBI network, that is an interferometer spread all over the world, connected antennas in a coherent way, so that when observing, they act as they are a single telescope with a diameter equal to the maximum distance between the two elements, called baseline. I'm also adding the VLBA, the very long baseline array, that is spread all over the US, and the very large array, because those are the interferometers that I used for the results I will present later. Of course, at other wavelengths, we can reach high angular resolution, but not at this level. But still, it's important to have a panchromatic view for understanding the issues that I presented so far. So this can give us the high angular resolution view that we need. However, to have a complete picture of these issues, it's not enough to observe, let's say, the brightest galaxies at high redshift, because they can be outliers and not representative of the entire galaxy population. So we need to observe the common galaxies that at high redshift are too faint to be detected in current surveys. For this reason, we need a boost in sensitivity, and this is given by strong gravitational lensing. Here I will just briefly recap what strong gravitational lensing is. So we have a distant background source, in this case a jetted AGN, and between us and this source there is a massive object, in this case a single galaxy, but it can be also a cluster of galaxies. So the light coming from the background source is distorted and magnified into multiple images just because of the presence of this massive object. And these multiple images that here you can see, they are extended and connected. They give us a high sensitivity and high angular resolution view of these distant objects that would not be possible to detect otherwise. So for this reason, gravitational lensing is a very powerful tool to study the most distant universe, all the components, and therefore start to understand better the interplay between stars, gas, and AGNs, but also we can get a lot of information on the deflector, so on the lensing galaxy, by using the lensed images to understand how the mass density distribution is at high redshift. And this is sensitive to both the baryonic and dark matter component. Therefore, that's a powerful way to address also dark matter issues. So in this talk, I will try to address these small-scale challenges in the lambda CDM model using strong lensing and high angular resolution observations. And in the first part, I will focus on the dark matter content in high redshift galaxies using strong lensing and VLBI, while in the second part, I will move to the source plane to study the baryonic content on parsec scales. And finally, I will try to address the small number statistics of radio loud lensing systems. So we'll focus on this part of the lensing system. So as I was mentioning at the very beginning, the missing satellite problem raises the question whether the dark matter is cold, as shown on the left, or warm. And this is just because of the number of subhalos or low mass subhalos that are predicted to survive the merger process, but we do not observe. These critical subhalos are at a level of 10 to the 6, 10 to the 7 solar masses. And you can see here, let me see if this works, like something, for example, like this. You can see here that they are very numerous. However, we can solve potentially the missing satellite problem by assuming a warm dark matter particle that creates subhalos that are less concentrated, and for this reason the lowest mass subhalos do not survive the merger process, and therefore we remain only with the most massive ones. Gravitational lensing can help us understanding this, and this is especially when using gravitational arcs, as for example in this case of 0751 plus 2716. These are global VLBI observations at 1.7 gigahertz at 5 milliarcsecond angular resolution and high sensitivity. And this sensitivity allowed us to recover the extended structure and faint structure connecting the multiple lensed images. So how do we do that? Here you can see a simulation of lensed arcs from McKinney et al. 2015, where we have an arc observed with VLBI and several like subhalos or different masses for each panel. So here we can see the direct effect of such subhalos on the arc that is breaking the arc, for example, in the last panel. So this can be seen only via gravitational lensing and VLBI, because the Einstein radii of such halos is at milliarcsecond level. So we can see only this. Of course, with this way, of course, detecting such subhalos would be extremely in favor of the dark matter, cold dark matter scenario. So what we did is to model 0751 arcs by assuming a smooth mass density distribution. We parameterized the lensed images, as you can see on the right. We have several lensed images identified, and this gives us a lot of constraints on the mass density distribution of the lensing galaxy, meaning that we can recover the parameters of the lens mass model at sub-percent level, and this is great and can be achieved only in these cases where we have several constraints. Among the parameters we could recover at high precision the inner mass density slope that we find to be slower than isothermal. And this can be interpreted as the lensing galaxy underwent a two-phase galaxy formation scenario, meaning that there is a first step where the gas-rich mergers are dominant and they lead to star formation, in situ star formation at the center of galaxy, and the dissipative processes of the star formation steepen the mass density profile. And then after this phase one, there is a phase two where the galaxy growth is dominated by gas poor mergers, and then it evolves into the passive galaxy that we observe now. And this is already an incredible way to study the evolution of distant galaxies by studying the inner mass density profile. Also, we compared the observed position, so the observed positions of the lensed images with the model predicted positions of the lensed images. And you can see this here in terms of milliarcseconds on the left and sigma on the right. And so some mismatch between the observed and model predicted positions is at 700 sigma, which is really significant, which is telling us that a smooth mass density distribution cannot reproduce the lensed images. And therefore, we need something more complex. And we would very much like to associate this with the subhalos that we need to solve the missing satellite problem, but it can also be due, for example, to line of sight perturbers as seen from the sketch from the Spali et al. 2018. So we may have galaxies along the line of sight that also can produce this kind of, we call it astrometric anomalies. Of course, a more detailed analysis of this is undergoing to understand what is the cause of this mismatch. But in summary, gravitational arcs and VLBI are really powerful to unveil important properties of high-redshift galaxies, for example, the inner mass density profile, which is already in favor for this kind of hierarchical structure formation model, but also they can unveil granularity at milliarc-second level, which could be due to satellites, galaxies along the line of sight, or even a more complex structure of the dark matter halo that we need to understand and address. So in the SHARP group, we are trying to search for luminous and dark satellites by using high angular resolution observations. And here I'm showing the near-infrared observations with Keck adaptive optics on the left, but also this is ongoing with ALMA spectral line from the method proposed by Stacy and McKee in 2018, and of course with VLBI that provides the highest angular resolution. So if you are interested in this kind of topic, I strongly suggest you to read these works where several methods are used to address these issues. So now I will move to the source plane that is shown here on the right to magnify the sub-galactic scales of distant galaxies. In particular, I will focus on the cold molecular gas in the first part, and this is because it's the key ingredient for star formation and supermassive black holes. Here you can see an hydrodynamical simulation at the center where the CO120, the best tracer for the cold molecular gas, is very much extended, but as I was saying at the beginning, it's at very low surface brightness. Therefore, what we generally do is to observe higher Gi transitions of the CO, for example, the 221, the 423. However, they do not trace the total cold molecular gas content, but they trace denser clumps, as you can see here at the center. So at the moment, the detections of CO120 are only for a few bright sources, which might be the tip of the iceberg of the galaxy population. And also it's very difficult to obtain spatially resolved observations of the CO120, which is necessary to test if we can see inflows of gas or rotating disks or merging events. So the epoch that can be the most interesting to study this connection between the cold gas and the rest of the baryonic content is that around redshift 2 and 3, and this is because there is the bulk, the peak of the star formation, the cosmic star formation, and the AGN activity. So with this in mind, we investigated 0751 on the left. This is the same lens system that I showed you before with VLBI, and B1938 on the right at redshift 2. So in these two systems, we detected the CO120 at very high significance with the VLA. You can see the green contours are tracing the moment zero emission of the CO120, which is very much extended. And here we are looking at the lens plane. So as you, maybe it's more clear on the right, this is very distorted into multiple lensed images of the CO. We have a very sensitive and multi-band data, complementary data on these two systems with Keck AO coming from the SHARP program, HST, and radio VLBI and radio VLA in continuum. So when we correct for the lensing effects, then we can start to see the intrinsic emission of these two systems. And here it is shown. You can see on the left 0751, where the cold molecular gas is extended for about 20 kiloparsec in projection. And at the center of the system, we have a complex structure where we have a very compact stellar core. You can see this in red here, traced by the Keck AO. And then this is hosting compact jets. And we have detected with the HST another component that might be a companion galaxy or a Lyman alpha cloud, just because the HST filter lies at the redshift of the Lyman alpha at 3.2. So this is a complex structure, and this compact stellar core is seen also in 1938 that you can see on the right, where we have this host tiny galaxy hosting a compact symmetric object. You can see this in the two hotspots here, and the cold molecular gas here is much more compact, extended for about 3 kiloparsecs in size. So the compact stellar cores observed at these redshifts are what we would expect as merger remnants from the hierarchical structure formation scenario. And also what we see is that there is a decrease in the intensity of the CO120 when arriving at the location of the AGN. This might be also an evidence for AGN feedback into the surrounding cold molecular gas. When we study now the velocity fields, the situation is quite complicated for 0751, where we detect multiple gradients that you can see indicated with A and B, and this is a very well resolved structure of the velocity fields at redshift 3.2. And on the right, you can see that in 1938, we have a much more coherent structure along the major axis of the cold molecular gas. This may resemble like a rotating disk, but of course dynamical studies are needed here to understand if this is actually a disk. But in summary, we find evidence for multiple gradients that can be indicating interacting objects or rotating disks at very high redshift. We found that there is a very large gas fraction also expected at those redshifts. So you can see this on the right. The gas fraction is of about 60%. But when we compare the CO luminosity with the infrared luminosity here, we see that our objects actually are lying at lower infrared luminosities with respect to the quasar population at similar redshifts. And this also might be taken as an evidence for AGN feedback in these two systems. Or it might be that there is a replenishment of gas in both systems via inflows or gas-rich mergers. And this is particularly true for 0751. So the take-home message here is that if we combine gravitational lensing with a panchromatic view of distant galaxies, we can unveil cold molecular gas fractions that are very large. We can start to see directly in spatially resolved AGN feedback at sub-kiloparsec scales. And in particular, all of this would not have been possible without the boost in sensitivity due to gravitational lensing. So I will just zoom in again into the very center of galaxies, which are very powerful laboratories to study the galaxy formation and evolution, and to be compared with simulations. And those parts are those related to the supermassive black holes and their area of influence. Here you can see a zoom in. But if the hierarchical structure formation scenario works as an intermediate stage of the merger processes, we should observe dual or multiple supermassive black hole systems. These systems that happen because of mergers should be surrounded by inflows of gas, because they should happen in the epoch where gas-rich mergers are very common, and these inflows of gas should be the fuel for both supermassive black holes, and also might be the cause of the triggering of the AGN activity. So this is very important to understand at high redshift how common these systems are, to see if this might be the way to trigger AGN, for example, or to make the AGN grow. So dual AGN systems look like a system on the left from a radio point of view. You can see we have two flat spectrum components that are the cores. We have extended jets that are misaligned. This is a very clear system, but we should also have two X-ray sources and multiple peaks in the narrow emission lines. And this is because each AGN is bringing together its own narrow line region. But this is the case where both the AGN are active. What if only one of the two is active? In this case, we may observe this system as offset AGN, as shown in the right, but offset AGN are a bit tricky because they can also be recoil supermassive black holes, or this offset might be due to an underlying jet. So offset AGN, it's not automatically a dual supermassive black hole, but one way to detect such offsets AGN is to compare the position of the supermassive black hole as traced here, for example, by the Chandra position in cyan with the peak of the host galaxy, as for example here done with SDSS. These kind of studies revealing offsets AGN, they are mainly limited to the local universe, and this is just because of the need of spatial resolution to find such offsets AGN. So strong lensing can really help us here, and this is guide showing how a small offset in the source plane, as shown in the top right here, where each symbol is separated by 1 milliarcsecond, can be very much enlarged in the lens plane. Also, for example, here by a maximum offset of 50 milliarcsecond. So this is much more easy to be detected with current facilities, and therefore this kind of systems at the highest magnification of in quadruple image lens systems are ideal to study offset AGN and potentially also dual AGN. So this is what we did for two test cases where we selected systems that have sensitive HST data and radio VLBI data, and also a robust lens mass density distribution, so lens mass model. One of the two is 0712. You can see the HST image on the left, where there are the 4 lensed images, A, B, C, and D, and the lensing galaxy G. The source is at redshift 1.3, while on the right you can see the VLBI view of this system with the very long baseline array at 1.7 gigahertz. And here you see the lensed images are mostly unresolved. So here already by eye, maybe you can see that there is a very good agreement between the radio and the lensing position. Of course, this is what we observe also in the source plane that is shown on the right. On the left, you can see the lens mass model. And so we do not find here an offset between the host galaxy emission and or the optical emission and the radio emission, as you can see here. But this is constrained at a very high precision here in the 17 plus minus 77 parsecs. So we are really into the very innermost part of the galaxies. The other system that we analyzed is class B1608, which actually is beautiful in the optical. You can see here the lensed images show these beautiful arcs. This is lensed by two lensing galaxies, G2 and G1 here. And it is at a similar redshift, actually, at redshift 1.4, the source, the background source. On the right, you can see the VLBI view with these compact sources. Maybe A shows a little bit of extension. But we find an offset, a marginal offset here between the optical emission and radio emission that is also, of course, recovered in the source plane, where we see this offset of about 215 parsecs between the optical emission and the radio VLBI emission, tracing the location of the supermassive black hole. So this is a good offset AGN candidate in the early universe. And if we put our findings into this plot, that is a nice figure from Bartlett et al. 2020. It was on Monday on AstroPH. You can see that if we plot the distance between the galaxy center and the supermassive black hole, here done for several surveys and searches with different techniques as a function of redshift, only gravitational lensing and VLBI and HSD can achieve the highest redshifts. And this is just because of the unique way to enlarge this offset in the distant universe. So this is a simple method, actually, that can be applied in a also more automatic way in future large surveys of lensing systems. And we expect 10 to the 5 lensing systems with the SKA, and if the SKA will have matched the sky areas, for example, with the LSST, then we will be able to study these systems in a statistical way in the distant universe. I would just like to briefly mention one finding from the last year by using multi-epoch VLBI observations that revealed the dual AGN candidate in the distant universe. This system is 2016 plus 1112. I don't have the time to go into the details of this system. It has a very complex lensing morphology. It shows 3 lensed images, A, B, and C. C is extended, and all the lensed images are resolved by VLBI. You can see in several subcomponents, and especially image C, you can see that there is this structure here and also faint emission connecting all these subcomponents. So this image is particularly important because it's at very high magnification. And the magnification is the highest for the radio loud lensing systems. It's of about 300, meaning that any small change in the lensing configuration would be more visible in this part of the lensing system. And this can be seen in this very basic GIF that I made on the bottom left, where we detect for the first time a clear proper motion in lensed images. And this respects the symmetry that that should be achieved via lensing. So our analysis revealed of the proper motions revealed that this must be, could be, a dual AGN candidate. For this reason, we are trying to understand this with multi-wavelength approach with VLT, ALMA, and the global VLBI observations at 5 GHz. And the proper motion that we detected here are at 3 milliarcsecond level per year. So it's they're really small, and that can be revealed only by using lensing. So if this were to be confirmed as a genuine dual AGN, then we can start to say that the statistics of finding lens dual AGN systems should be order of magnitude higher than what's predicted currently. So that's why it's really important to find these systems in the distant universe. So the take-home messages of this part is that gravitational lensing plus multi-band high angular resolution observations and multi-epoch VLBI observations are very powerful tool to find dual and offset AGN in the early universe. And this is needed to understand the statistics of these systems and can be applied to the entire radio loud population. So I just would like to take 2 minutes to talk about what I'm doing right now in Bologna. That is another application of strong lensing. And this is to understand where the most violent emissions that I showed you in the very first video from the last simulations happen. So in the Fermi Large Area Telescope showed that the blazars dominate the extragalactic gamma ray sky. And these systems, this AGN, are do seen at a very small viewing angle, as you can see here. So the jet is pointing towards us. So they give us the unique opportunity to look directly into the central engine and understanding the processes of this extremely bright flare or ejecta, how the ejecta are happening to the AGN jets. It's really important to be then implemented properly into simulations. So we need to understand what are the processes going on here. However, we do not know yet where the gamma ray emission happens in blazars. It might happen very close to the supermassive black hole or several parsecs from the central engine along the jets. In this case, we should expect, after a very bright gamma ray flare, to detect also a delayed radio flare and potentially also a new knot moving through the jet. These kind of knots with superluminal motions are quite often observed in AGN jets. How do we do that with lensing? So this time we will use gravitational time delays. So if we have a powerful flare happening in a distant blazar, and this blazar is gravitationally lensed, the flare coming from the background source will happen at different times in each lensed image. Here we have only 2 lensed images. So you see that the signal arrives first in one image and then in another image, and the gravitational time delay will tell us where the location of this emission is at very high redshift. Here you can see the Fermi-Lat view that cannot spatially resolve the lensed images, but it has a very good time resolution. Therefore, autocorrelation studies, function studies can actually determine the gravitational time delays. And if the gamma ray gravitational time delay is compatible with the radio flare gravitational time delay, this would mean that the radio and the gamma ray flare actually happen in the same location. If not, this will mean that the 2 flares, the 2 radio and gamma ray emissions are separated, and via lens modeling we can actually say by how many parsecs, for example. So in April 2019, we had this, we detected this very bright flare with the Fermi Large Area Telescope, and this is among the 5 brightest events detected by the Fermi since its launch. You can see this on the right. From the system that is PKS 1830, you can see the Merlin image on the left. It shows a beautiful Einstein ring with 2 lensed images. So this is only one of the 2 gravitationally lensed blazars that are also gamma ray loud. So there aren't so many opportunities to study the location of gamma ray emission and radio emission by using the method that I showed. So we followed this up with the VLBI, with a very long baseline array at 15, 24, and 43 gigahertz. And you can see this here on the right with the light curves that happened, these observations happen right after the gamma ray flare, where we detect some features. In particular, we use the 43 gigahertz light curve that is the most densely sampled to estimate the radio time delay. Just a comment on the left, you can see the zoom in on the lensed images A and B with the VLBA at 43 gigahertz. Here the angular resolution is of 0.3 milliarcsecond, so this is very high. And so we use this light curve coming from this 43 gigahertz data. We found a time delay of about 16 days, which should be and must be compared with what derived at the gamma ray wavelength, which is still undergoing. So stay tuned. We will compare this in near future. And if the 2 time delays will be compatible, this will mean that the 2 emissions are cospatial. Otherwise, they will be not. So radio loud gravitational lensing systems are really powerful to test the current hierarchical structure formation model at the smallest scales that are the critical scales to start to discern between cold dark matter, warm dark matter models, or different AGN feedback, different supermassive black hole formation models. So we really would like to have more systems because of all the advantages that they have, which I summarize here. So we have very high angular resolution, microarcsecond astrometric precision on the lens images, which means that we can constrain the lens mass model at very high precision, but also we can detect very small proper motions in the lens images. There is no dust obscuration nor microlensing from the lensing galaxy, and also it's very easy to monitor the lens images separately, and so estimating the time delay. However, we have very little statistics, and today we know only of about 35 radio loud lensing systems, and this is a combination of the rarity of the lensing effect and the fact that the radio loud AGN are only a few percent of the total AGN population. So we searched for this new radio loud lensed AGN in the MGI-20 VLBI survey that you can see on the left. This is a large survey at VLBI scales with a very long baseline array at 1.4 gigahertz. This is an example of a pointing. And by using simple selection criteria based on lensing arguments, we found two lensing systems that are a rediscovery, and they are shown on the top right here from the class survey. And the other systems, we followed them up with the C-band observations with the VLBA, and we found two final lens candidates. So this method is observationally efficient because we start directly from the VLBI scales where we can already spatially resolve the lens images, and therefore we skip all the intermediate steps at lower angular resolution that, for example, have been done in the past with the VLA for the class survey. So, and also the VLBI follow-up at C-band, thanks to the very large bandwidth of the C-band, we can really test the spectral energy distribution of the two lens images. This is what I'm showing here for one of the two candidates, where you can see the imaging at the three observing frequencies, 1, 4, and 7 gigahertz, while the 4 and 7 gigahertz have been obtained simultaneously. So you can see the spectral energy distribution on the right of the two lens images. This is a good candidate, especially because of this, because the two SEDs actually are very similar with different amplitude that is predicted to be, because each lens image would be at a different magnification. So one would be at a higher amplitude than the other, so A and B are red and blue, but we are looking at the same background object here, so the SED should be the same. So this is a very good lens candidate, while the other has not been detected at C-band, and so we cannot rule this out as a lens candidate. So we use this to estimate lensing rate, that is this one shown in the slide, that is consistent with previous results, even though we have very large uncertainties here. But if we apply this lensing rate to an all-sky survey with a VLBA with the similar characteristics of the MGI-20, then we would expect to find hundreds of radio loud lensing systems. So with these numbers, we can already start to discern between cold dark matter and warm dark matter models, for example, by using quadruply image lens systems. We can start to find more exotic systems like dual and offset AGN, and understand it better, the connection between the baryonic, all the baryonic components and AGN, if these systems have also complementary multiband data. So of course in the future there will be the SKA, and we expect to find 10 to the 5 lensing systems. And I really like this quote that is, in the future there will be more future. So when the SKA will arrive, we will discover new things that we do not know, or maybe we will even see lensing configurations that are too rare to be observed right now, but might be very suitable for some science cases. And VLBI, I hope that I convinced you that VLBI can really help us understanding what's going on in these systems, understanding better the physical processes in these sources. So the SKA VLBI part will be fundamental to follow up those systems that are more suitable for each science case. So here I leave you with the summary. Thanks a lot for your attention, and I stop here.
Okay, thank you very much, Cristiana. Thank you very much. And we have already some questions for you. So the first question that I'd like to ask, there are actually two from the same person, and I thought we could combine them. One is, which is more important for constraining lens models? The position accuracy of the images or images with more rich features? And the other part of the question is, how do you separate structure changes caused by a lens or caused by the source itself?
Okay, these are very good points. And so as for the first part, the most important part, for example, in the case of the arc, it was this very good radial coverage of the lensed images around the Einstein radius. So the more lensed images we have around the Einstein radius, the better the lens modeling is constrained. But also we should have some, let's say, radial structure, ideally, of course. If we have also this, the radial structure going towards the center, then also the inner mass profile can be constrained even better. So lensed images that cover the entire Einstein radius are very powerful to do that. And also how to discern changes in the lens plane or in the source plane. So this can be done using lens modeling. So for just as an example, in the case of 2016, we tested whether the motion of the lensing galaxy could reproduce the position of the lensed images, and it could not. So at the same time, it could not reproduce all the positions, while a position in the source plane could explain the positional change observed in the lensed images. So this is a way to discern between the two. Also, the motion of the lensing galaxy should have been extremely like superluminal motion to be able to reach some kind of agreement, and that's not physically correct.
Okay, thank you very much. Another question we have from another participant is, can you explain the observed AGN offsets in surveys in some more detail? And this is referring to a figure in the new paper that you showed. How was the result obtained? And this person suggested the offset is getting quite large and maybe seems to correlate with redshift. And could it be a limitation in the technique used rather than a real offset?
Okay, so I think he refers to this figure here. Let me, yeah, so here, yes, there is this kind of correlation here. They're actually plotting only the observations. And so the scatter here is quite large, as you can see. So it's very hard to say that this is a tight correlation as a function of redshift. From our point of view, our points, for example, have been not used to constrain any of their results because they're not, they are only 2 points, so they're not statistically enough. But I think that towards what you say, our points actually are bringing down this offset as a function of redshift relation. Meaning that if we have enough spatial resolution, then we can start to see that there is no correlation. This might be a possibility. And so I do not know the details of all of the surveys shown in this plot. Some of them are, for example, Barrow's 2016 is that I showed at the beginning of this part where they compared the Chandra versus the optical position. Then there is the Lena 2014, I think, yes, this point here where they use the HST, quasar, and optical light. So this is just a comparison between observations. And so these are different methods, while in our case, yeah, it's only based on the offset in the lens plane that will apply also to offsets in the source plane. So I'm not sure if I replied to the questions. I would be happy also to talk more about this.
Okay, thank you. Okay, we don't have any more questions to be answered in the question and answer box. So if you have some, please send them in, or if any of the speakers whose questions have been answered have further questions to ask, please add those. But I also have a question about the later part of your talk, Cristiana. It's a very interesting question. This idea of comparing flares in different images, the time delays and time delays, say, between radio and gamma. What kind of techniques can you use to try to make sure that the flares that you're comparing really do correspond to each other?
This is a very good point, and I think this is the most difficult part, is to understand what kind of feature in the radio light curves corresponds to the gamma ray flare. So of course, like cross correlations or correlation functions to study the two light curves can be quite useful, but indeed in the ideal case, if we have a very dense sampling in the light curves for a period that precedes and also goes after the gamma ray flare, then it would be ideal to understand this better. But yeah, from a statistical point of view, this can be done. In our case, for example, we see these features, tiny features in the light curves that cannot be immediately associated with the gamma ray flare, especially if we compare, let me see if I can go to the light curve, the increasing influx density. So yeah, here. So here at the end of our observation, we see an increase in flux density. So it's really hard to say if this tiny emission variability is due to the connected to the radio flare, or if the end of the light curve is connected to the gamma ray flare. Sorry. So this will be done I think in a statistical way by comparing it with the Fermi Large Area Telescope light curve. But in, for example, the time delays can tell us if the two emissions are, let's say, correlated, for example, by a spatiality argument. So if the two time delays will be compatible, then there is a good chance that the radio and the gamma ray emissions are cospatial and therefore might be correlated.
Okay, thank you. And we have another question that has come in. How is polarization affected by the lensing? And can you get any more information by making polarization observations?
This is a very nice question. So polarization is preserved by the lensing effect. So we should observe the same polarization in, for example, in the jets of the lensed images in all lensed images. Of course, when this is not the case, it means that something in the screen is affecting the polarization. So it gives a lot of information on the lensing galaxy. And this, for example, has been done nicely in the last years by Ivan Martí Vidal on this system on PKS 1830, so this one on this slide, and it can tell us a lot about the what is going on in the screen, the lens plane. So, for example, it can reveal if there is a disk galaxy, if we can trace the polarization on the lensed images. So that's important to know. Of course, we can also understand it better once we can correct for the lensing effect how is the polarization in distant AGN jets, and therefore start to understand if the properties of impolarizations, for example, are similar in the early universe and in the local universe. So this is a good point.
Okay, thank you. And we have another question also about 1830. Is the radio monitoring of 1830 continuing? And this could be of interest, particularly because it looks like something interest has just started at the end of the observations that you show.
Yeah, alas, the monitoring didn't continue, so we are that's absolutely true. So when I looked at the data, I thought the same, but it was too late to continue the monitoring already. But we are planning to monitor this source with VLBI in the future to not miss this kind of opportunities, because this system is very active at gamma rays. So at the moment, no, there is no monitoring going on, but that's our plan for the next years to do it with VLBI, so that we can really start to compare gamma rays and radio VLBI emission.
Okay, thank you. Okay, if there are any other questions, I'll wait just a few moments and see if there are other questions coming in. Okay, I have one that's come in. Are there any plans to get some IFU data for MG 0751 and determine whether it is a Lyman alpha illuminated cloud?
Yes, this is in our plans. So to apply for VLT Muse that has the best, also best angular resolution to study this, and indeed that's a good point. Yeah, that's in the plans. That would really help us understanding what's going on in that optical component, if indeed it's a Lyman alpha cloud or it is something else.
Okay, thank you. Do we have any more questions for Cristiana? Okay, thank you very much, everybody, for taking part in this webinar, both to the speaker for a fine talk and for the many questions that came in. And just before leaving, I have had a request from Zsolt Paragi to maybe advertise an EVN document that is coming out, VLBI 2030, a scientific roadmap for the next decade, the future of the European VLBI network. And there's a link there, and I'll put this into the answer live category, and I believe that should then appear to everybody. Okay, so thank you again very much for participating, and we look forward to having many of you again with us in a couple of months' time, sometime in September, for our next talk, which will be given by Yuri Kovalov of the Astrospace Center in Moscow.